In our explorations of probability theory so far, we've considered several different modes of convergence for sequences of random variables. The strongest is almost sure convergence, which was the kind of convergence we saw in the strong law of large numbers. We've also had use for convergence in LP, for p between 1 and infinity, and also convergence in probability. These are ranked roughly in decreasing order, where this is the strongest and this is the weakest, although there aren't strict implications this way without some additional assumptions. One thing that's important to note about all of these notions of convergence is that they really heavily depend on relationships between the random variables themselves, not just the individual distributions of the random variables. For example, almost sure convergence means that the limit of xn is x with probability 1. And as we know, that statement is a statement about a tail event. So although we don't actually need to know anything about the distribution of any fixed xn, we do need to know about their tail sigma field, and so in some sense their joint distribution for all sufficiently large n, in order to reason about almost sure convergence. Now LP and convergence in probability don't require as much information, but they still require information about the joint laws of xn and the putative limit x. Convergence in LP means that the LP norm of the difference between xn and x tends to 0, or the pth power of it if we prefer. That's just the expected value of the difference between xn and x to the pth power, and we can use the change of variables formula for the pair xnx to write that as an integral with respect to the joint law of xn and x. Similarly, convergence in probability can be expressed in this kind of form. Convergence in probability means that the probability that xn minus x exceeds epsilon tends to 0 for every epsilon, and that we can write as this integral with respect to the joint law of xn and x. One way or another, all of these notions of convergence require us to at least know about the joint distribution of xn and x. And that can be more than we can handle if we have limited information about the joint distributions of our random variables. So we're going to introduce in the next lectures some different notions of convergence that aren't convergence for random variables per se, but are convergence for measures. And so we will talk about convergence of the distribution of a random variable to some other distribution, a notion which will depend only on the individual distributions of xn for each n. The first and most straightforward such notion is called total variation convergence. If mu n is a sequence of probability measures on some fixed measure space, which I'm calling SB because we're probably thinking of these as the laws of some random variables taking values in some state space S. Let's just think of these measures as functions defined on this space B. And so we can use any notion of convergence for functions that we like. We could use pointwise convergence or the stronger uniform convergence, which is what total variation is. We define it in terms of a metric. If mu and nu are probability measures on this fixed measure space, then their total variation distance is defined to be the maximal distance between their values at any element of the domain. That is, we take the difference that mu and nu assign to any event, and we look at the supremum over all of those absolute differences. Now we can import this notion to then talk about total variation distance between random variables just by saying that the total variation distance between x and y is defined to be the total variation distance between their distributions. In other words, it's the supremum over all measurable sets B in the range of the absolute difference of the probability that x is in B minus the probability that y is in B. Now we're going to explore several cases where this is a very natural notion of distance between probability measures. Before we get there, let's start by proving a core lemma about how to calculate total variation distance, which will be useful in all of our foregoing calculations. This is a version of what's called Sheffe's lemma. And it's about the case where the probability measures have densities with respect to some fixed reference measure. Suppose that alpha is a finite measure on the same fixed measure space, such that our two measures, mu and nu, are absolutely continuous with respect to it. Therefore, by the Radon-Nikodym theorem, they have densities, let's call them u and v. In that case, the total variation distance between mu and nu is exactly equal to 1/2 the L1 distance between their densities. We'll prove this straight from the definition fairly straightforwardly. Fix any measurable set b, and look at the difference between mu of b and nu of b. Well, because of the presence of the densities, we can calculate that as the integral over b of u d alpha minus the integral over b of v d alpha, which of course, by the triangle inequality for integrals, is less than or equal to the integral over b of the absolute value of u minus v d alpha. And analogously, let's do the computation for the difference between mu of b complement and nu of b complement. There, we'll get the same thing with a b complement. But notice that because mu and nu are probability measures, mu of b complement is 1 minus mu of b, and similarly, nu of b complement is 1 minus nu of b. And so the difference of mu of b complement minus nu of b complement in absolute value is the same as the difference between mu of b minus nu of b. Therefore, if I add these two up, I just get twice the distance between mu of b and nu of b. And that's going to be, by what we proved here, less than or equal to the integral over b of absolute value of u minus v plus the integral over b complement of the absolute value of u minus v. But those add up to just the integral over the whole space of u minus v absolute value, which is the L1 distance between their densities. And so that's where the 2 comes from here, and that gives us the upper bound. To prove the lower bound in here, we just need to show that since we're taking the supremum over all b, that we can find some set, which I'll call A, for which the equality is achieved. And the set A that does the trick is the set where u, the density of mu, is bigger than v, the density of nu. We can just calculate as follows why this works. First, note that the integral over the whole space S of u minus v d alpha must be 0, because it's the integral of u d alpha minus the integral of v d alpha, and both of those give 1, since they're probability measures. Now let's break that up, as we did above, as the integral over a plus the integral over a complement. Now the set A is precisely the set where this is positive, and a complement is precisely the set where this is negative, and so we can rewrite that as this in terms of absolute values. Therefore, since this difference is 0, these two are equal, and so following the framework above, we see that the difference between mu of a and nu of a is, again, the absolute value of the integral over a of u minus v. But because on a, u minus v is positive, we can move those absolute value bars inside. And that's also equal to the integral over a complement of the absolute value of u minus v, as we just showed. And therefore, adding those two up, we get that 2 times the difference between u and mu of a in absolute value is equal to the sum of these two terms, which, as we argued above, is equal to the integral over all of S, which is just the L1 norm. And so we do see that the inequality that we proved here is actually saturated, and in the supremum we get equality as claimed. Now that might seem like a limiting statement because it only applies in the case where we can find such a positive finite measure with respect to which both of the measures are absolutely continuous. But in fact, we can always do that. And actually, we can do it even with a countably infinite family of probability measures. Just like this. If I have any countable collection of probability measures, I can take a sum of them like this. There's nothing special about these coefficients. We could have taken any sequence of positive real numbers that adds up to something finite here. This is a new finite measure. I've arranged it here to be a probability measure, and we do get that each of the individual original measures is absolutely continuous with respect to it. The reason, of course, is that this is a sum of positive terms, and so if on a set A this equals 0, that sum of positive terms has to all equal 0, which means that each mu n of A must equal 0. Therefore, we have absolute continuity. And therefore, by the Radon-Nikodym theorem, each of those measures has a density, uk, with respect to this measure alpha, where of course uk is non-negative and integrates to 1. So as a nice application of this fact, we're going to prove the following theorem. Total variation distance is in fact a metric on the set of all probability measures on the space SB, and in fact it is a complete metric. Now, this can be proved directly without use of Sheffe's lemma that we're going to use here, and the fact that it's a metric is really a very straightforward thing to prove directly. But the completeness is a bit hairy to prove and actually boils down to the same way that we proved completeness of L1. So why not just use the fact that Sheffe's lemma allows us to identify this, for a fixed sequence anyway, as a subset of L1. So here's our proof. First, it's fairly obvious that total variation distance is non-negative and symmetric. We need to see that it's non-degenerate. So suppose that the total variation distance between two measures is 0. Well, once we've fixed this reference measure alpha with respect to which all of the mu's, in particular mu1 and mu2, are absolutely continuous, we can write this as 1/2 the L1 distance between u1 and u2. And we know that that being 0 implies that u1 equals u2 almost surely. Now we should be a little careful here. That's almost surely with respect to alpha. But because mu1 and mu2 are both absolutely continuous with respect to alpha, this implies that they're equal almost surely with respect to mu1 or mu2 as well. And that means that the measures mu1 and mu2 that have those densities u1 and u2 must be equal as measures. So total variation distance is at least non-degenerate. We also want to see that it satisfies the triangle inequality, and that's just going to be following directly from the triangle inequality for L1. This is the L1 distance between the densities u1 and u3, and by the triangle inequality for L1, this is less than 1/2 of the distance between u1 and u2, plus the distance between u2 and u3. And again, by Sheffe's lemma, that is equal to the total variation distance between mu1 and mu2 plus the total variation distance between mu2 and mu3. And so we see that total variation distance really is a distance. It's a metric. Now, what about completeness? Here we're going to leverage the completeness of L1. So if I have a sequence mu n that is Cauchy in total variation metric, meaning that the total variation distance between any two terms in the sequence tends to 0 as n and m go to infinity, well, by Sheffe's lemma, that says that the L1 distance between their densities goes to 0 as n and m go to infinity. In other words, that says that the densities form an L1 Cauchy sequence. L1 is complete, as we've proved, and so therefore un converges to some u in L1. And so we're going to set mu to be the measure which has that u limit as its density with respect to the reference measure alpha. Now that mu is a new probability measure. Why? Well, the function u is an L1 limit of these un's, and therefore, as we've proved, there is a subsequence of the un's that converges almost surely to u. All of these are non-negative, and that means that u is almost surely non-negative, so it is a non-negative measurable function. And we can check that it is a probability measure simply because L1 convergence implies convergence of integrals. That is, this difference is less than or equal to the integral of the difference, which tends to 0, but this is constantly equal to 1, And so that says that this fixed number converges to 1. So we have a probability measure here, and if we take the total variation distance between mu n and mu by Sheffe's lemma, that is 1/2 the L1 distance between un and u, which by construction goes to 0. That shows that our total variation Cauchy sequence has a limit, which is a probability measure, and that shows that this set is indeed a complete metric space with respect to total variation distance. Another nice application of Sheffe's lemma is a dual representation of the total variation metric. If h is any bounded random variable on our common measure space, then for any two probability measures, we can bound the integral of h against mu minus the integral of h against nu by the supremum of that bounded function times the total variation distance, with an extra factor of 2 there, as we should be accustomed to right now. And in fact, we can redefine the total variation distance to be the supremum of all such differences, where we take all possible bounded measurable functions whose supremum is 1, with the necessary factor of 1/2 here. We'll prove this again by fixing a reference measure with respect to which mu and nu have densities u and v, and then we can just calculate. The difference of the integral of h against the two measures is the same as the difference of h times u minus h times v against the reference measure alpha. By the triangle inequality for integrals, this is less than or equal to the integral of absolute value of h times absolute value of u minus v d alpha. And of course, we can factor out of that the supremum of h. And by Sheffe's lemma, this integral is exactly twice the total variation distance between mu and nu. That proves the first part of the result. And in particular, that means that if I take any measurable bounded function whose supremum is less than or equal to 1, then the absolute value of the difference between the integrals of h against mu and nu will be less than or equal to 2 times the total variation distance between mu and nu. And that provides one inequality here. To prove the reverse inequality, we use the exact same saturation argument that we gave in the proof of Sheffe's lemma. That is, if we define h to be the indicator of the set where u is bigger than v, minus the indicator of the set where u is less than or equal to v. Well, since the sets where u and v are greater or less than each other are disjoint sets, this difference of two indicator functions takes values either plus or minus 1. So it is bounded by 1 in absolute value, and we can check that the difference of the integrals of that function h is exactly equal to this. And this has been organized so that in these two terms, this makes this positive, this makes this negative. And so the negative sign here means that we will get the sum of the two terms, both having integrand absolute value of u minus v over the two sets, u greater than v and u less than or equal to v, but those two sets form a partition of s, and so this is just the integral over all of s of u minus v, which is twice the total variation distance by Sheffe's lemma, and that shows the reverse inequality. This dual representation of total variation distance will be important when we start considering how it relates to other forms of convergence of measures that we'll be considering in the next couple of lectures. Now I'm going to tell it to you straight. Total variation distance isn't the most useful notion of convergence of measures due to some deficiencies that we'll see in future lectures. But there is one situation where it makes a lot of sense, and that's where the sample space of the random variables considered is finite or countable. Indeed, there's a very nice simple formula for what total variation distance is in that case. If S is countable, then for any two probability measures mu and nu on S, the total variation distance between them is simply the little L1 distance between the probability mass functions. And from there, we see that convergence in total variation distance in this discrete setting is just equivalent to convergence pointwise of the probability mass functions. Let's prove this. Again, we're going to use Sheffe's lemma, which applies just as well in this discrete setting. So fix a reference measure with respect to which both mu and nu are absolutely continuous. And let's let alpha k denote the probability mass function of that reference measure. Then, of course, we can recover the reference measure as just the sum over all values in S of point masses of those probability masses at the points k. And so we can compute that the total variation distance between mu and nu by Sheffe's lemma is 1/2 the L1 distance with respect to that measure alpha between u and v, the densities. But how do we integrate with respect to a discrete measure like this? That's just the sum. Now we bring the alpha k inside, and then we simply note that in this discrete setting, d mu equals u d alpha just means mu of k is equal to alpha of k times u of k. So this is mu of the singleton k minus nu of the singleton k, which gives us our formula here. Now to prove the second statement of the lemma here, well, one of those directions is quite straightforward. Indeed, if the sum over all k of mu n of singleton k minus mu of singleton k tends to 0, then it certainly follows that each term in the sum of finite terms tends to 0. So that proves the forward direction. The reverse direction seems like it ought not be true. Just because we have a sequence of terms here that each converge to 0, why should their sum converge to 0? And it's actually not hard to cook up examples of positive sequences of real numbers for which that reverse implication fails. But this is no regular old sequence of positive real numbers. These are probability mass functions. And so we can use some of the tools of measure theory to prove this. That's going to be on your homework. Now that we have a simple way to compute total variation distance between discrete measures, let's finish out this lecture by computing some total variation distances between some important discrete probability measures. For example, suppose that I take two Bernoulli probability measures with different means, p and q. By what we just showed, the total variation distance between them is the sum over all values, of course there's only two of those, of the probability mass functions, times 1/2. Well, that gives us 1/2 of 1 minus p minus 1 minus q plus p minus q, and both of those are equal, and so we just get that the distance between a Bernoulli of mean p and a Bernoulli of mean q is p minus q in absolute value. That's pretty nice. How about Poisson distributions? Remember that the Poisson distribution is the measure on the non-negative integers whose probability mass function is e to the minus lambda times lambda to the k over k factorial. So how about the distance between two Poisson distributions with different means? Well, that's going to be the little l1 distance between their probability mass function sequences times 1/2. And then we can stare at that for a little while and try to simplify it. But unless we are very talented with combinatorial calculations, we're not going to see much structure come out of there that's useful. The result, which is useful, and will come up later, is that this is less than or equal to lambda minus eta. And that is going to be on a future homework set, leveraging this calculation here and Poisson approximation of these, which is a topic we'll get to next time. Meanwhile, a calculation we can do more explicitly is the difference between a Poisson and a Bernoulli of the same parameter p. So that's going to be the little l1 distance between their probability mass functions. Now, when k is bigger than 1, these terms are all 0, and we just have the terms in the probability mass function of the Poisson, and so we can separate out those two first terms as follows. Now let's first deal with the last term here. That's basically the sum of all of the probability masses for a Poisson, which of course would be 1 since it's a probability measure, but we have to remove the first 2. And so that's equal to that. And for the first ones, we have explicitly these two terms here. And let's just note that 1 minus p is actually always smaller than e to the minus p for p between 0 and 1, as you can easily check with some calculus. And so this all adds up to these terms here. And simplifying that, we get a relatively nice expression, p times 1 minus e to the minus p. There is the total variation distance between a Bernoulli p and a Poisson p. Notice that when p is close to 0, this is even closer to 0. How much? Well, we'll see and use next time that this is smaller than p squared. Before moving on to other notions of distance between measures, next time we're going to use some of the calculations we just did to prove a quantitative result about Poisson approximation, sometimes called the law of rare events. And we'll use that to motivate another topic which is quite relevant in the realm of total variation, coupling arguments.